Hello everyone, welcome to the solutions for problems 1 through 4. Okay, I would like it to remind everyone that the best way to learn from these problems is to give them an honest try yourself and then go ahead and look at these answers and the solutions. So, problem 1, a ball relatively low density is thrown upwards because of air resistance. Because of air resistance, the acceleration while traveling upward is negative 10.8 meters per second squared. On the trip downward, the resistance is the opposite direction, and the resulting acceleration is negative 8.8 meters per second squared. Where the ball reaches the level from which it was thrown, when the ball reaches the level from which it was thrown, how does the speed compare to which it was thrown? Okay, so basically for this problem, you want to consider the ball going up with the acceleration negative 10.8 meters per second squared, and then when it comes back down, negative 8.8 meters per second squared. And the way you want to think about this is you want to realize that in both cases, the ball travels the same displacement, the same distance up, same distance down, except one is accelerating at a larger rate. Okay, so this is a very fast speed when it starts, and it slows down to a final velocity of 0 at the top, and then here on the way down it starts with a 0 velocity and then travels the same distance down, just with a smaller acceleration. Therefore, this one has to have a smaller final speed than this initial speed. Okay, that's because they traveled the same distance. One was accelerating at a larger magnitude, one was accelerating at a smaller magnitude. So if you think about it like this, I like to think about it like a car. Okay, so if they both started at 0, okay, both started with 0 speed and then accelerated for a certain distance, okay, except one's acceleration was 10.8, the other one's acceleration was 8.8, and said they both went the same distance, and I asked you which one would be faster at the end of that distance, the answer would obviously be the one that was accelerating for the longer period of time. Now, this is a more complicated example, but it's basically the same question. Both have a 0 velocity at one point, and then they accelerate to a different speed, or accelerate away from a different speed. And so the result is that on the way up, it has a faster velocity than the way down. So B is the same, no, not the same, is less than the original speed upwards. C, okay. A parachute jumps out of an airplane. A parachutist jumps out of an airplane and accelerates with gravity to a maximum velocity of 58.8 meters per second in 6 seconds. So quite the acceleration. Then she pulls the parachute cord after 4 seconds and has constant deceleration. Descends to 10 meters per second for 60 seconds. Reaching the ground from the height when, from what height did the parachutist jump? So, in this problem, you want to realize that there are 3 situations that are occurring, okay? There's the first section where the parachutist is accelerating up to speed. There's the next section where the parachutist is pulling the chute and decelerating, and then there's the last section, which is the longest, where the parachutist is moving at a constant velocity, okay? And so they gave us timelines for each of these. So this first section, where she's accelerating, took place in 6 seconds. The next one took place in 4 seconds, where she pulled the chute. And then the next one took place in 60 seconds. And then they gave you indications for the velocity for each of these. So initial velocity at the top is 0, but then after that first 6 seconds of acceleration, the final velocity is 58.8 meters per second. Now, as soon as we start the 4-second interval, the new initial velocity is now this 58.8. Okay, and then what happens? It slows down, 58.8, slowing down until 10 meters per second at the end of those 4 seconds. That's when she pulls the chute. Then she keeps those 10 meters per second all the way to the ground for 60 seconds. And so now the goal is to figure out the displacement for each of these sections. And then if we can do that, add them up. That's the height at which she started. So for this first section, I have VI is equal to 0. VF is equal to 58.8 meters per second. The acceleration of the fall is just gravity, so negative 9.8 meters per second squared. And I have to solve for distance. Hold on one second, I'm going to grab a calculator. Very good. All right. So, looking at these variables, is there a equation that connects all these variables? Absolutely. VF equals VI plus AT. VF is 58.8 meters per second, and that's equal to 0 plus 9.8 times the t of 6 seconds. So solving, is that true? I forgot I'm solving for distance. So this equation is not good. D equals VIT plus 1/2 AT squared. Much better. Actually has distance in it. So clearing that out, multiplying by 2. So 2D over T squared. I'm sorry, solving for D. Very smart of me. Okay, so actually solving for D. So I just need to figure out 1/2 AT squared. So 1/2 9.8 times 6 seconds squared, giving me 0.5 times 9.8 times 36. So this first section has a displacement of 176.4 meters. Okay, so pretty far for 6 seconds. Now, the next section, we want to find the displacement again, and we want to find the displacement again. The initial speed is now that 58.8 meters per second. The final speed is 10 meters per second. We don't know what the acceleration is, but we know the time is equal to 4 seconds. So we need an equation for displacement here, and I'm pretty sure I know one. Average speed is equal to distance over time, but I don't have the average speed, but I can figure it out, because average speed is just adding up the final plus the initial, divided it by 2. If I set that equal to d over t, I can multiply both sides by t, and I can solve for displacement. So 58.8 meters per second plus 10 meters per second, all in parentheses, divided by 2, multiplied by the time of 4 seconds, gives me my displacement. So 58.8 plus 10 divided by 2, and then times 4. So this next section, she traveled 137.6 meters. This last section is going to be the easiest. She had a constant speed, so I could just take distance equals velocity times time. And so the average velocity was 10 meters per second, and the time where it took place was 60 seconds. And so therefore, 10 times 60, 600 meters is the last one. So now I just got to add all 3 of my displacements up for the final answer. So 600 plus 176.4 plus 137.6. That gives me a grand total. Can't do this one in my head. 137.6 of 914 meters, which I believe is option A for the problem. All right, next ones are not going to take as long. So for number 3, find the resultant of 2 vectors, 50 units due east and 100 units 30 degrees north of west. So we want to figure out the resultant of these 2 vectors. Now, this problem sounds complicated if you don't remember how to do vectors, but it's important to remember that it's just very simple. So let's think about this in terms of a person walking, okay? So this person's going to walk, if I set up a compass, north, east, south, west. This person's going to walk directly east 50 units. Okay, we'll make those units meters just so that we're used to them. Okay, And then they're going to walk 100 units northwest at 30 degrees above west. So 30-degree angle here. They're going to go from where they just finished. They're going to go northwest 100 units. So 100 meters. And the question is, where did he, if you could do the same walk in a straight line, okay? So if you can do the same walk as this guy just did with one straight line walk, what direction would it be in and how far would he have to walk? That's the question. And it comes down to a triangle question. So basically what we want to do is we want to figure out the sides for this triangle. Then we can solve for this angle and the length of this side. So the way we do that is we leave the 50 and we have to break the 100 apart. So I'm going to draw the 100 vector by itself, okay, as its own triangle. Now, when he walked 100 meters northwest, he walked a little bit west and he walked a little bit north. And we can figure out how far in each direction he went. So sine of theta is equal to the opposite side over the hypotenuse. Okay, so if we want to solve for the opposite side to this 30-degree angle, I just have to do this formula. So hypotenuse sine of 30 is equal to the opposite side. So I plug in 100 for my hypotenuse, sine of 30 degrees. That should be equal to 100 sine of 30. That's 50 meters, or 50 units. So that means that they went 50 meters north. Now, how far west did they travel? So that would be cosine. Cosine of theta is equal to adjacent over hypotenuse. So hypotenuse cosine of theta is equal to the adjacent side. 100 times cosine of 30 degrees gives me 86.6 meters. That's how far that one traveled. Okay, so now let's go back up to the picture. Okay, so he went 50 meters this way. But then with the 100 meter, he went 86.6 meters this way. So if we cancel out the 50 meters here, we're only left with 36.6 meters west. So that's how far west he went. And then we saw that he went 50 meters north. So this has to be 50 meters north. So I've got the two sides to my triangle. So our answer is going to be the solution for this smaller triangle here, where we have 50 meters north, 36.6 meters west, and we're solving for this angle and this side. So I'm going to take tangent of theta in order to get the angle. So tangent of the angle is going to be equal to the opposite side of the angle, which is 50, divided by the adjacent side, which is 36.6. All right, and so I inverse tangent, so I will second tangent 50 divided by 36. That'll give me 54.25. So the angle that I'm looking for is 54.25 degrees. So that's the angle. And now I just need to find this side. So I can take either sine or cosine and solve for the hypotenuse. So sine of theta equals opposite over hypotenuse. And I can rearrange this to solve for the hypotenuse. So that would be opposite side divided by sine of theta. So 50 meters over sine of 54.25, giving me the final answer. Equals 61.6 meters. So I'm looking for 62 and 54, which is option D. Okay, so last problem on this first page. John throws a baseball from the outfield from shoulder height at an initial velocity of 29.4 meters per second at an angle of 30 degrees with respect to the horizontal. The ball is in its trajectory for a total interval of 3 seconds before the third baseman catches it at an equal shoulder level height. Assume air resistance is negligible. What is the ball's horizontal displacement? So, the ball's going to do this. All right. Initially launching at a 30-degree angle with an initial velocity of 29.4 meters per second. And they want us to figure out the distance that it traveled like this. So I'm going to set this up. dx equals vixt plus 1/2 axt squared. So we want the horizontal displacement. And so there's no acceleration in the x direction for any projectile. So that just goes to 0. And so all I need is the initial velocity in the x direction, and I need the time. And so to find the initial velocity in the x direction, I have to look at the initial velocity that's being thrown at this angle, and I just have to solve for the x component of that. So if this is 30 degrees, I just need to solve for this side of my triangle, and I will have my answer. So the adjacent side, this is going to be cosine. The adjacent side of my triangle is going to be equal to 29.4 meters per second times cosine of 30 degrees. And so that's going to be 29.4 cosine of 30. Make sure your calculator's in degree modes. And we have 25.46 meters per second. And so that means I've got 25.46 multiplied by the time that they gave us was 3 seconds. And that means it's going to be just over 75. 76.4. 76.4 meters is the final answer, which is option A.